So welcome to the seminar in the Gemini Center series on quantum computing. Today we have Alexander Stasik, who will give a presentation on quantum reservoir computing. His background is that he has a PhD in astroparticle physics from the Humboldt University in Berlin and the German electron synchrotron DSE on high energetic neutrinos from core collapse supernovae. He then did a postdoc in computational neuroscience at the Department of Physics at the University of Oslo. And this was followed by a researcher position in bio-inspired artificial intelligence. Now he's a researcher in analytics and AI at the Department of Mathematics and Cybernetics at Syntif Digital. So he will give a presentation on quantum reservoir computing. And without further ado, take it away.
Thanks a lot for the introduction. So I'll go through the idea of quantum reservoir computing, giving it a little bit as a summary about the field. Please feel free to interrupt me at any point. Since not everyone has a background in machine learning, I think I'll start by introducing reservoir computing as a machine learning concept. So the idea behind reservoir computing is that you have a reservoir, which is typically a recurrent neural network structure, or more general, a complex recurrent dynamical system. And you drive it with a certain input, and then you have a linear output based on this reservoir. And what you do in the training process is that you only optimize this output, or this weights to your output of your network. So you treat this reservoir itself as a black box. You randomly initiate it with some properties that it has an interesting dynamics. And in the training process, you just feed in your input data through this network, and you only optimize the linear output of it. And this works with general loss functions, so typically a mean square, but you can also put everything in a reinforcement learning setup or any type of setup what you want to do. And as this reservoir, you can basically use any type of high-dimensional complex system. And it's treated as a black box, so it's randomly initialized, but weights are never optimized. So the entire machine learning part is basically down to solving a linear problem with the output. And the advantage of those approaches is they're extremely fast and extremely simple for implementation and for training. And they are very, very general. So they have been shown to basically have the same properties as deep neural networks, as general function approximators. Basically the trick is that all the complexity of this modeling comes from this reservoir. And generally it has been applied to many different fields. So originally the idea of reservoir computing comes from neuroscience, where it's called liquid state machines. And there the idea is that it's somehow a model for the brain. So that the brain is a very complex dynamical system. And if you learn something new, you basically just only learn how to interpret the output of your system. There are different flavors of reservoir computing, and there's something called extreme learning machines, which is where your black box reservoir is just a feed-forward structure. Then the typical standard approach is recurrent network structures, and these are called echo state machines, but also generally reservoir computing. And it has also been applied to quantum neural networks, and I want to talk about this today a little bit more. An advantage is, since you really don't need to know anything about this reservoir here, you only need to basically feed in and get an output. You can also do this on real-world physical systems. So, well, typically it's studied or simulated with artificial neural networks. You can use any type of complex dynamical system that you find in the real world. basically motivated that nature can do computations really fast by just following the laws of physics. So it has actually been shown that you can literally use a bucket of water where you drive and initiate waves on the surface and use this as a liquid state machine. But also applications are like 2D quantum dot structures, but also use gate-based quantum computers. So any type of complex systems you can simulate in a computer or find in reality, you can use as your reservoir. And I will go a little bit into the reservoir quantum computing idea. So I said before, you replace the reservoir with a quantum network. And then what you do is you optimize a fidelity-based cost function. Technical advantages is your quantum computer, your quantum reservoir does not need to be able that you can control any weight. So you don't need all this fine tuning that you have for a gate-based computer. And it also works with classical and quantum input. So this is indicated here on this plot where it's just the same plot as shown before, but colorful to indicate the larger properties of quantum systems. So it has been applied to a variety of systems. I'll just give here a brief overview and with corresponding references. So one advantage, of course, is if you drive the systems in a recurrent mode. So you feed some information into your quantum system, then it has a certain memory properties. So kind of like a recurrent neural network structure. So it has been used for modeling chaotic systems, like Lorentz oscillators and very well understood mathematical systems, but also like on classification tasks. And I just put the references here. This has been extended to really work on real world time series data. So people are trying to predict stock markets and other natural phenomena. What has also been shown is, and I want to discuss this now a little bit, is that these quantum reservoir computers are universal in the sense that they can mimic and basically are equivalent to gate-based algorithms that are implemented on a standard quantum computer setup. And what's also been done is random quantum neural network, random quantum circuits have been built on IBM existing quantum infrastructure. So if you follow this reference here for interest, what they did is they just used this IBM infrastructure and put together random circuits and then used this as a black box machine, which of course is not the smartest way to do this, but for a systematical study. So to go in one of these realizations, this is from a paper where they showed this universal reservoir quantum computing property. So what they built is the reservoir, quantum reservoir, is just a random two-dimensional fermion lattice with some tunneling property. And this is like a standard model. So here you see the Hamiltonian. And the system is then driven with a classical input. And here, typically what's done is that you just apply a laser to stimulate the system. And as you can see here, the system is it's just randomly generated. So you don't need any fine tuning in building this quantum reservoir. And the only thing that is then later optimized is this coupling to your input qubits. So we have this random system here. It's described by this Hamiltonian. And then you add an interaction term with your input qubits. And these needs to be fine-tuned. And these are then the linear parameters that later on are optimized. So they used this and try to use this reservoir setup to build to test on standard quantum gates. So this is just basically you compute the time evolution and you discretize it on retard times, and then you compute the fidelity. And what you see here is the results where they used a random network, and I think this was for two random nodes here. So they didn't really have a very large setup, only two nodes that are randomly coupled. and then they learned the coupling to the inputs to reproduce these 4 quantum gates. And what I want to mention here, it's always the same reservoir system. So they initialized it once randomly, and then they just had 4 different outputs they learned, but the system is the same. So it's not like you need 4 different reservoirs.
So can I ask a question?
Yeah, sure.
So really, I don't understand what is shown in these graphs. So you have this kind of reservoir,
yeah,
and you tell that it was the same always. It was not changed. So what has changed between the different?
They changed these couplings here. So these 4 coupling matrices. So this terms here.
Ah, so okay. So when you say the same network, it's not the same. It is the same structure, but with different couplings.
Different input and output couplings. But the reservoir itself, this structure here, is E and Ks. They are fixed.
They are fixed. Okay.
So what you do is you build this model once, or you implement it in a hardware system, and this can be arbitrarily large. And then for each task, you only learn these inputs and the outputs. So yeah, sorry that I was a little bit imprecise kind of slang. So that the network I would consider as this part here only on top. And
yeah, then I think I understand it.
And yeah, this is frozen.
And you train it by running many inputs and comparing to the desired output and optimizing these J couplings.
Yeah, so you optimize fidelity. And basically this is the result from after training. So yeah, to clarify, you get like 4 sets of J's for each problem here.
Yes, yes.
Yeah. And of course, it relies on the problem that you need to generate the training data, but that's could be realized. Similar, they tried to learn a larger quantum circuit, so the Grover's algorithm with 3 inputs. So here's just the input they used to learn the data, and then to generate the data. And then they feed this into the same structure and just learn the linear in and outputs again. And here you see the result after adjusting the input and output weights. And there's in the paper they also generalized this to show that in principle, if you have a large enough reservoir, which has some general constraints on its dynamics, so it doesn't have like a trivially simple dynamic. You can approximate to arbitrary precision any quantum circuit or any quantum algorithm you can come up with. And this somehow brings me already to the summary. So quantum reservoir computing is like a version of classical reservoir computing where you rely on or benefit from the large phase space of quantum systems. And to build this, it's way easier to build a basically fully programmable quantum computer on equal size, because you require less control about all the connections between your qubits. One of the problem is it's like a machine learning approach, so you don't really come with all the guarantees that you have if you have a proper algorithm that you just implement. And you also require training data. While as the training itself is very easy compared to standard problems in machine learning. And you can implement this on any dynamical system that you come up with. So you can use a random existing gate quantum computer, or you can construct more general quantum systems like a 2-dimensional fermion grid, for example. And the status is that a lot of people, I think, are looking into this, and basic statements have been made, and as shown here, people applying this to more and more academic problems, but I haven't seen any large-scale application, but this could also be to the limitation of existing hardware. because while you have this random here, this network here at random, still you need to be able to fine tune these input weights. So you need some kind of control about your system. Yeah.
Okay, so first of all, thank you for the interesting presentation. I guess I have at least one question. So you probably expected the question as well, because it's a standard question. If you compare the classical version of this reservoir to the quantum version, are there any claims or insight of any advantages? Or, I mean, one obvious advantage I see is if the input data is quantum, then it could be an obvious obvious way to show that there, or to predict that there might be an advantage. But are there any other things that are known about this?
I haven't seen really one-to-one comparisons. I mean, one advantage is that you have this exponentially growing phase space due to your quantum system. But since the framework is so general, it also really depends what you use as a dynamical system. So I think there's some constraints and some results for neural network structures, recurrent neural network structures for classical reservoir computing. But in principle, you can use any system that you also find in nature. So I think there are no general claims why that this has an advantage except for this exponentially growing phase space. But it's, I mean, it's sitting in between. You can use this on current and near future quantum devices. So it's like an intermediate technology.
Okay, thank you. Are there any more questions?
Yes, I also had a question. If you can go back to these 4 alternatives. So they were, oops, yeah, there it is. So they are all classical, is it true?
I think here they...
No, I mean, the question is, when they did it, did they use inputs that were quantum states, meaning that they could be superpositions of the determine classical input values, and outputs that also were superpositions, or they were just classical bit input output?
I would have to check in the paper, but if I remember correctly, they used quantum input.
And output also?
Yeah. But I would need to check with the reference, and I can send you the reference as well.
Mm-hmm. Mm-hmm. Yeah, to me, this is a bit new. I'm a bit puzzled by the whole thing, because it seems then that this reservoir, it has inside it information about any function that you like to calculate whatsoever. I mean, you use the same reservoir in all cases. Yep. So you decide afterwards, after you constructed it, you decide which function you are going to make it look like. Yep. So it means that in principle, it contains all functions in its somehow information about all possible functions that you can, and only the way that you read out this information determines which function that you are evaluating somehow, which is a bit puzzling.
Yeah, it's a little bit, I mean, the idea might be a little bit similar to support vector machines, where you have a very high dimensional parameter space in which you can in principle perform any function in a linear way, or any cut in a linear way. And that's somehow the idea behind here. So in practice, in classical reservoir approaches, you have very high dimensional dynamical systems.
Yeah, so when I say that it's any function, it is a kind of low dimensional function. It's a small function, and this high dimensional function, if you like. I mean, this reservoir, it computes some very high dimensional complicated function, and you read out only kind of section through it, or some way that you simplify this to read out only a much smaller, I don't know what a smaller function means, but so you mean that this high dimensional function, it contains in it all possible kind of low-dimensional functions that you could wish to evaluate. Okay.
Yeah, makes sense.
One more question, because machine learning is somehow about going from a small known data set to a more generalized. I mean, you somehow can extrapolate outside the data that you trained on, right? So how does this scale with, let's say I learn this thing on Grover for 4 qubits, and then I want to do it for 40 or 4,000. Do I have to retrain it for every instance, or does this somehow naturally generalize for the larger systems?
If you scale dimensionally of input and output, you would need to retrain. Because you just have this linear weight matrix, and if you have more bits, you don't know what to do.
And how does the learning scale with respect to the number of qubits?
It's a linear learning problem, so you can just apply it as linear regression.
Okay. Are there any more questions?
Yes. You had some references? Could you?
Yeah, I can also send these references later around.
I'll just take a screenshot.
Yeah, I can. I have the. I mean, yeah, that's fine. I can also have the reference properly, so then it's easier to find. But yeah.
Okay, thank you very much. It was a really interesting talk. A lot of food for thought.
Yes, I guess there are no more questions. Then we thank you one more time, and we'll meet next time.